Okay, today's video is about assessing normality, which really means that if you have a large data set that you've collected, or you've researched some data that someone else has collected, it'll be important for you to figure out if it's normally distributed or not. And in this video, I'm going to show you some ways to help you determine whether or not your data is normally distributed. But first, I need to take care of a little business. I've had some requests for color in the videos. So here it is. Here's your color. Okay, moving on. So if your data set's large and we want to determine whether it's normally distributed, and by large I mean you have more than 30 pieces of data that you've sampled from a larger population, there are a couple ways to tell. And the first one is that you can plot a histogram and you can analyze the shape and make sure that it is normal or approximately normal, because nothing is ever perfect in real life. So a histogram, if you remember, is kind of like a bar chart. You plot on the x-axis, you plot your values, and then along the y-axis, you plot the frequency of those values. And you can see in this case that if I were to draw a smooth curve around that shape there, hopefully it doesn't move this time, just like if I were to lay a string around the outer edge, that looks probably about normal. There's you could also use the empirical rule. That's the 68, 95, 99.7 rule. And you could check to see how many values lie within those standard deviations. Remember that 68% of your values should be between one below and one standard deviation above. 95% of your data values should be within 2 standard deviations, and 99.7% of your values should be within 3 standard deviations. But when you have a small set of data, then you have to check out your data another way. And by small set of data, I mean less than 30 values. So the way that we check a small set of data is we create a normal probability plot and we analyze it. A normal probability plot is just a plot of your data. There goes that screen moving again. Let me put it back. All right, so a normal probability plot is a scatter plot of your data. So on the x-axis, you would have whatever your data values are that you're looking at. Those would go on your x-axis. And then you would calculate an expected z-score for those data values, and that would go on the y-axis. And you would plot the corresponding values, whatever they look like. So your x-axis is the observed data values, and the y-axis is the expected z-scores. So the steps for creating a normal probability plot are: first you need to rank your data. So by rank your data, I mean you need to put it in order from smallest to largest. And that's called an index. I equals 1 would be the smallest data value. I equals 2 would be your second smallest data value. And so on. The second step is to compute using your index value I minus 0.5 or 0.5 divided by n. N is the total number of data values you have. And I is your index value. Oh, that sounds, oops, that's an N. I'm trying to write cursive so you don't hear that annoying clicking on the screen of my iPad pencil. I don't know why it does that. Okay, and then the third step is to solve for alpha. I know there's a lot of simple symbols and letters here. Eventually you're going to get really familiar with alpha and n. We probably won't see index so much, but alpha you're going to see a lot of. So alpha is going to be 1 minus whatever you got in your last value. So I minus 0.5 over n. You only need to do that step once. You just subtract it from 1 after. You're going to use that for z alpha, and remember that that's the value of the area to the right. And then your fourth step is to compute the z-score that goes with that. Now you can use a table for that, or I recommend using your calculator. And in your calculator, it would be inverse norm. Area to the right. So if I have a z alpha of 0.1, then I'm looking for the top 10%. Remember, alpha is the top percentage. Okay, so I'm going to calculate a little bit for you. I don't want you to write this down. We're going to actually do a normal probability plot in class, but I wanted to show you how it's done. Just watch. You don't need to write it out. I didn't give you room in your notes for that, but I wanted you to have some idea of how it's done. So you'll note that in the first column I have my values indexed from 1 through 6. I have 6 data values from Greyhound racing finishes. And I'm going from smallest to largest. My smallest value, you'll notice here, is 31.6. The next one is 31.35. And they get larger until I have my highest value of 32.52 seconds. So in the next column, I'm going to calculate my index value minus 1/2 divided by the total number of data I have. So that first column, is the index value. That's I. 1 minus 0.5 divided by n is 6. And when I calculate that, I get about 0.1. Well, actually, it's 0.09, but for the purposes of this, we'll just call it 0.1. And then this next value would be 2 because that's my index here, 2, minus 0.5 divided by 6. And that gives me a value of 0.25. And then I do the same thing all the way down, 3 minus 0.5 divided by 6. If you're doing this in a calculator, you need parentheses around the top to protect your fraction. And that gives me a value of about 0.42. And then I'd have 4 minus 0.5 divided by 6 gives me a value of 0.58. 5 minus 0.5 divided by 6 gives me a value of 0.75. And 6 minus 0.5 divided by 6 gives me a value of 0.9. And if you look, these are going to be kind of symmetrical. Here I have 0.42 and 0.58 in the middle, and those add up to 1. The next ones are 0.25 and 0.75, and they add up to 1. And the top and the bottom also add up to 1. All right, so I'm going to subtract those values from 1. 1 minus 0.1 is 0.9. 1 minus 0.25 is 0.75. 1 minus 0.42 is 0.58. 1 minus 0.58 is 0.42. And 1 minus 0.75 is 0.25. And finally, 1 minus 0.9 is 0.1. So I'm looking for z of 0.9, which is the top 90th percentile, or another way to say that is the bottom 10th percentile. And then here I'm looking for z 0.75, z 0.58, z 0.42, z 0.25, and z 0.1. So the top 90th percentile, or the bottom 10th percentile, the score for that is negative 1.28. Right? I've got 90% of the area is to the right. It would look like that. So it makes sense that that's going to be a negative number, 1.28. And then z alpha 0.75, that means that 75% of that area is going to be to the right. And I get a z-score using inverse norm of 0.75. Actually, it's going to be z alpha 0.25. And I get negative 0.64. And z alpha 0.58 is the top 58th percentile, or the bottom 42 percentile, or 42nd percentile. And I get a z-score of negative 0.2. Here I'm going to get a positive 0.2, a positive 0.64, and a positive 1.28. So when I plot this, these observed values here are going to go on the x-axis, and these z-scores here are going to be my y-axis. And here's a picture of what it looked like. Okay, I have at roughly 0.2, I have a value here and a value here. And these are my finish times. This is my x-axis finish times. I have 31.5, 32, 32.5. That's my scale. So these values are plotted. These are the x values, and these are the y values. This is my second. This was the index of 2, index of 3, index of 4, index of 5, and my index of 6 is up here. So what we're looking for in a normal probability plot is we want these values here to roughly follow a straight line. The straighter the line, the better. There can be a little bit of wiggle, but generally it has to form a straight line. And that's called a strong linear correlation if it looks like it has a straight line. In this case, it's pretty straight. It's a little bit of wiggle here, over here, and a little bit here, but like I said, nothing is ever perfect in real life. Here's some examples of some normal probability plots. So these have a little bit more data. Okay, a lot more data. These have 100 pieces of data, but if you look at this first one, it is all the plots are almost exactly on that line. I mean, there's a little bit of wiggle here and there, but nothing too big. If you look at this second one over here, you'll see that these values here and these values here really stray off that line, especially the ones up at the top. And the same thing here. I've got these values that aren't staying where they should be. These indicate not a normal distribution, that these two graphs here are not normally distributed. This one though, this one looks pretty good. So that's it for this topic. We'll talk about it more in class where we'll create a normal probability plot. So bring your laptop with you to class next time.